Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, thank you. I'm honored to be here. So a BCI, or a brain-computer interface, is a device that enables communication without movement. More specifically, it enables users to send messages or commands without movement. The main application of BCIs so far has been with severely disabled users. So although some users with moderate disabilities can use other types of assistive communication systems, such as those based on eye tracking or sip and puff switches, some people are not able to use any interface requiring movement. And thus, instead of getting information from motor activity, you instead have to get that through direct measures of brain activity. So most BCIs translate your brain's electrical activity, or EEGs, into messages or commands. So to provide a brief primer on how this works, neural communication produces electrical activity. So if you have a single neuron there and it fires or communicates with another neuron, it sends a pulse of electrical activity down the neuron. Now, if this occurs with a single neuron, you can't really pick that up on the scalp. However, if you have millions of neurons working together to do a certain task, you may be able to pick up that activity from electrodes placed on the scalp. And so this slide here shows some conventional electrode caps, the left one from EEGs and then the middle one from Neuroscan and ElectroCap. And these have some drawbacks that are familiar to most people. Not the least of which is the delightful need for inserting gel in there, which is really fun, especially when you're recruiting subjects who have hairdos. And the need to put on 256 individual channels and this sort of thing. So this is a major reason why BCIs have historically not been as popular for the mainstream market, aside from bandwidth and other issues I'll get to. However, this is one area that's seen a great deal of progress of late. Newer EEG recording systems, field recording systems, have a lot of advantages over these earlier approaches that were only meant for laboratory work. They require less or no prep time and skill, so whereas the systems before might require a trained experimenter and 20 minutes or more to get the electrodes in the exact right location and squirt gel into each one of them and wiggle them around like this, oh, I got that finger movement down, and get the impedance on each site, this requires basically just putting something on your head. They require less gel or no gel. So very recently, we've seen a lot of progress with dry electrodes that you just put them on your head and they work. So in addition to not requiring prep time and hassle, it also doesn't require any cleanup. They also require fewer electrodes. They're more portable. They handle artifacts better. By artifacts, I mean outside noise sources, which are very prevalent in an environment like this. They're wireless and they're cheaper. Cost is coming way down. So the left image is a field recording system from a company called Quasar, and you can see that what they've done is incorporated a couple sort of pods of 5 of their electrodes into a gamer mic. And this is an example of a dry electrode. I'll show it more on the next slide, that doesn't require any prep time. The middle one is from a company called B-Alert, or Advanced Brain Monitoring, up in Carlsbad, California. And they've done a lot of work with fatigue and alertness monitoring. And so this is a wireless baseball cap. They have one sensor over the parieto-occipital area here and one in the frontal midline, and it's a self-gelling electrode. So you put it on and it releases gel until it gets a good connection. So it does require gel, but it doesn't require an experienced operator. And then the other one is just a simple headband. So this is maybe the simplest of the ones here, but works. And this is just something that my friend Jamie Pineda built in a short period with a couple electrodes around the lab. And he actually used this in a study. So he has a paper out in which he described people using these in a field setting with this very simple headband and moving a cursor around. Yeah.
Breakthrough that enabled this to happen. How do these work?
Good question. There are a few reasons why these are becoming more viable. Let me go to the next slide a bit. In the case of the Quasar electrode, what they're doing is you can see that there are actually 3 concentric rings of protrusions there. What most electrodes have, such as these individual electrodes on these, is there's a little metal disc and there's some plastic and a metal disc inside there, and you're squirting gel in there in order to get a connection between that metal disc and the surface of the scalp. If you didn't put gel there, the impedance on that individual site would be so bad you couldn't get a good recording. One of the things that these guys have developed is these 3 concentric rings that are getting lots of noisy signals, but using filtering in order to reduce the noise. And then if you look at this image here, you see they have a sort of a pod of 5 concentric rings. So in a sense, you're getting double spatial filtering in order to reduce noise. In addition, the person from Quasar who gave me these, Rob Matthews, said that they've made some materials developments. So they have different kinds of some kind of, rather than metal, a plastic alloy sticking out there that they're able to record data better. And so that enables this sort of approach here where you could embed these sensors in an audio headset or glasses or other things that are already worn on the head. So this gets at a major concern about BCIs, which is, well, people don't want to put something on their heads. Well, they do if it's easy and you don't have to squirt gel in their hair and have someone like me around to do it. Another approach, sorry, go ahead.
It says wireless, so how many channels can you get over wireless? Seems like you need a lot of bandwidth. Plus you get interference on
No, that's a good question. The amount of bandwidth you're actually sending with EEG data is not very much. It's on the order of maybe a half K per second per channel. So if you had a 2-channel system with 1 K per second, you can get some pretty good information about brain activity. So the bandwidth requirement is fairly low. It depends on a lot of things like your sampling rate and the number of bits and such. One of the advantages of wireless systems is that a common source of noise in wired systems like these is cable movement. So if the subject is sitting there and moves his head or is playing a game or walks around, that's going to induce a lot of electromagnetic activity in the wires. And so wireless systems, although they have their own drawbacks, at least avoid this noise source. Other questions? All right, so another way that you can record EEG activity or brain activity is through invasive recording. In other words, electrodes placed underneath the scalp through surgery and are actually in contact with neurons, or at least underneath the scalp very close to them. And these, of course, have a lot of theoretical advantages in that you can get more information and better spatial resolution, but of course have the drawback that they require surgery. And so I'll talk more toward the end of the talk about the difference between invasive and non-invasive approaches. In addition to the EEG, there are a variety of other ways to measure functional brain activity. A very popular one lately is called functional magnetic resonance imaging, or fMRI. That's the left image. You can also get magnetoencephalography, which is basically measuring the brain's magnetic activity more than electrical activity. PET scanners are around too. I don't have a picture of those. They haven't really been used for BCIs. And a newer approach called functional near infrared, or FNIR, that essentially involves shining light that penetrates the scalp, bounces off your brain, and returns to a sensor, which is kind of a cool technology. It's safe and painless, and you literally put a sensor here, and it's bouncing light off your brain in real time. However, as I mentioned, most BCIs today still use EEGs, don't use other approaches. And there are a variety of reasons for this, but the main one is that most of these other approaches, as you can see, are not very practical for everyday use. fMRIs and MEGs in particular are very expensive. They cost millions of dollars. They require a huge mechanism. They require a trained experimenter, and so on. fMRIs induce other problems. You can't have any metal on you. I worked in an fMRI lab down in San Diego, and we had this checklist that we would read off. You know, do you have any earrings, implants, pins, neurostimulator, pacemaker, belt, anything like that? And we ran through the checklist, and we had a subject there, and she started to yell as we were moving her into the machine, and it turned out that she was wearing a wire bra that was being sucked up by the magnet. So that's just one more thing that underscores problems with practical use of fMRI. EEGs don't have any such limitations, of course. FNIR is a somewhat more promising approach. The cost is somewhat lower, on the order of tens of thousands of dollars, and it's much more portable and easy to use, and so I'll talk a bit more about that later. But again, most BCIs today, and probably in the near future, continue to use EEGs as their primary tool for imaging brain activity. All right, so I'll move on to the question of sort of what these EEGs are doing. In other words, what are you thinking about? And one of the most pervasive myths in the BCI literature, or in the public perception, is that BCIs are operating according to some sort of wiretapping or mind-reading metaphor. That is, that if you think a certain word, like you think the word hello or you think the word yes, that's actually literally echoed in there, that you have neurons that are saying that, and if you just stick a microphone up close enough, you can hear that. And that's absolutely not how BCIs work. And it would be great if we could build something that way. That's by far the most intuitive way to build such a system, is that you think a word or you think a certain thing and that appears on the screen. But so far we haven't been able to do that. There have been a great many efforts where they have people think two different words or different images or something. It's very difficult to separate. However, this is a very popular notion in science fiction. So there are a lot of stories that present BCIs with this sort of operating metaphor, that they're sort of a very high bandwidth system, they're completely immersive, whatever you think, they just sort of pop up. And although I realize this audience probably doesn't think of BCIs that way, that we realize the Matrix is fiction, it's still a pervasive metaphor. A lot of people think of things that way. One exception is the Star Trek thing, just for nerds in the audience, on the off chance there are any here at Microsoft. The Star Trek, the cage, is right on par with modern technology. So that's the wheelchair BCI that can move in 2 dimensions and answer yes or no. I could build that in about a month. It's right about the limit of what we can do now. So kudos to them. They're only off by about 40 years. And there are, of course, more BCI stories there. Another thing is these often portray BCI people as being extremely evil. So it's ethically okay to chop them up with axes or something because they're trying to change your personality. And of course, most of us are nice guys. So to clarify, BCIs cannot read your thoughts. Just got to say that again. And also, they can't operate without your knowledge. So the idea that you could have something across the room that would pick up your brain activity, again, if we could do that, you would have seen it already. BCIs can't write to the brain. That's a different field called computer-to-brain interfaces, which I'll be happy to talk about. But the idea is not that you're changing brain activity. You're not making them do something or sending them a message or writing an image to the brain. You're just reading activity. And finally, they can't repair injured areas. So if you're disabled, this is only circumventing the area rather than actually improving function. This may be changing. Denny Profit, for example, has been doing some work with rehabilitation in BCIs, that maybe you could train people to have some improvement. But at the moment, they're used really just for replacing damaged areas rather than restoring them. And also, I want to throw out some other approaches that people may have heard about, but that are not BCIs because they don't enable communication. In other words, a BCI by definition lets people send messages or commands, and so a lot of these are just sort of passive monitoring approaches where you're measuring activity that the brain produces anyway, but not necessarily an intentional volitional command being sent by the user. And I'll talk more about these other BCI-like systems later on, because certainly activity in this space is very relevant to BCI development. So, enough about what they aren't. What is a BCI? Well, BCIs rely on certain voluntary mental activities that we can pick up. In other words, the field has been driven largely by what's been known about EEG research, driven more by basic science than the application side so far. One thing that has been known for a while is that we can detect EEG activity associated with selective attention. So if you were to look at this matrix here, and you could think a certain letter, like the letter N, we couldn't necessarily pick that up. But if I were to ask you to focus on one of these letters and count if it flashes, then we could detect that. So we could tell, for example, whether you're paying attention to a certain letter or a certain event or ignoring that. BCIs can also operate based on imagined movement. So, for example, people might imagine golfing to move a cursor up, or tennis, or whatever activity they're familiar with. I'll talk about this shortly. Or they might relax to move a cursor down. Some BCIs also use emotional imagery, so people might think about strong emotional events. Sometimes sexual imagery is effective. This works with a type of BCI that uses slow cortical potentials that I'll get to later. And finally, some BCIs operate based on certain distinct mental tasks. So people could think about rotating an object versus doing a math task versus singing If I Only Had a Brain. We could pick that up from EEG activity. All right, so next I want to present a short video here that shows one of these systems in operation. This is a type of BCI called the P300 BCI. It starts in a few seconds, and I'll explain how it works. So this BCI utilizes selective attention. What happens is you'll see the user viewing a matrix of letters and other characters, and each of these is flashing. So the system flashes one row or one column at a time. and the user is trying to spell BCI. So you may not be able to see it as well, but in the corner there it says BCI, and then the letter B is in parentheses. And the user is silently counting each time the letter B flashes while ignoring all other events. Now you may notice that the system is going through this quite a few times. In other words, it's not just flashing each row or column once, it's flashing each row and column 15 times. So given 6 rows and 6 columns, it requires a total of 180 flashes to identify an individual target letter in this system, which is several years old, and I'll get to that. So you can see now it's just worked. So the user has spelled the letter B, and the letter B appeared on the top left part of the monitor. And now the user is concentrating on the letter C. So same row but different column, and same task, is silently counting each time a letter flashes. Now another comment I want to make is that this is using a conventional cap. It's an older cap, and so this is another problem with publicity sometimes, is they'll show people using this cap and people assume, well, you have to use a 64-channel cap to get that. In this study, they're using only one electrode on the cap. So the one sort of right behind the bundle of cables, which is called site PZ, the parietal midline site, is the only one in use. Now you can see they just spelt the subject spelt the letter C, and so is now moving on to the letter I. So this gives you an idea how a BCI works, that via selective attention, simply choosing to pay attention to or count other certain stimuli, you can determine which stimulus is of interest.
Are they also looking at the letter, or are they just fixating at some point and just paying attention on the side?
In this particular study, they were looking at the letters. So one of the issues that's come up with this particular approach is, as you suggested, that it requires eye movement, and thus it might not be effective for patients who are not able to use with gaze control. This has been a big issue I've been studying over the last few years, and what we have found is that if you don't shift your eyes but simply shift your attention without shifting your eyes, which is called covert attention, you still get the effect. It's not as dramatic and may require a little bit longer, but we have had systems like these working with patients who are not able to shift gaze. So the short answer is that shifting your eyes helps but is not necessary. Yeah.
Like if patients can move their eyes, then what is the feedback that they're getting that they are achieved what they want to? Like how the communication goes the other way around?
Well, the usual feedback that they get from the system is that it presents the letter that the system thinks that you just spelled. So it's not shown here, but a lot of systems have a backspace option or something if an error comes up. So that's the feedback to the system.
You can move your eyes, you can focus on the letter.
Right? No, if you... Right, it's still in your field of view, so they can see the whole screen, and that's one of the things we found is that larger displays don't work with patients who can't shift gaze, as you suggest. A 6x6 does seem to work, but is perhaps at about the limit. We tried a 10x10, and it did not work. So, and of course, to clarify, it probably varies a lot across subjects. So some subjects might have better visual ability. Perhaps people who have a lot of experience playing games might be better at visual attention tasks. So it's a wide open field. I mean, it's still a fairly new research field, and in particular, taking these to patients and exploring them in the field is something that's really quite new. But preliminarily, it seems that 6x6 is about the most you can handle without gaze shifting. As another comment, you can also develop this using auditory stimuli. So there was a paper out released earlier this year in which instead of having anything visual, they would simply play words. And so they would present the word yes or the word no, and there was a pause of 1 second before each one. And you asked the subject to silently count the word yes or the word no, and that also worked. So you would get this brain response called the P300 if they were counting the word yes, and so you could ask a question and get a response. The drawback of that is it's much slower, because one advantage of this visual domain is it allows you to compact the stimuli in 2 dimensions. So instead of having to flash 36 things, you only have to go by 12. Of course, instead of flashing individual rows and columns, you could also flash half the screen at a time, which is what I did in my PhD thesis. It was one of the studies to explore that. So on the one hand, there's a lot of basic science left to be done, and that's part of what makes the field so much fun. But on the other hand, it's moving along quite quickly. There's a lot of work. Consistent with that, I was saying that this system takes roughly 45 seconds per letter, so a little bit less than that. And that may give the impression that that's the best we can do, which is not really the case. So, for example, you see this graph here in which I'm describing the time to an accurate signal. And this applies only to this type of BCI that I was describing, where the blue line here is an EEG-based system and the red line describes a keyboard or a headset or a conventional system, where the time to get an accurate signal is maybe a fraction of a second. But in the video I showed, it took about 45 seconds per letter. And I know a little bit later in 2000 and 2002, as we were playing with it, we got it down to about 30 seconds. And then the same lab that developed this video, the Walpole lab, a few years ago, in 2004, I think, reported it being down to about 15 seconds. And it's getting much faster. I saw in their lab an unpublished thing where they got it down to about 10 seconds with 100% accuracy. Largely what they're doing is improved signal processing. So what the challenge is that if you look at a single trial, it's very noisy. It's very hard to distinguish them. And so these early classifiers here were using simple linear approaches. You basically just take the sum of EEG activity in a certain area. I'll get to that in a second. And now they're using more advanced approaches such as neural networks that are accounting not just for that information but also frequency information and other info in there. And this is rapidly progressing. But this is the time for an accurate signal just for a P3 BCI. There are other types that I'll show later in which you can get a response in well under 1 second. Another field in which BCIs are making great progress and related systems that record EEG is prep and cleanup time. So as I mentioned, this is a really exciting thing where it used to require maybe 15 minutes or more to put a cap on someone's head. And with these dry electrodes where you just simply put on a headset or a cap, it's basically down to the same as a headset. So the red line might reflect a headset where it takes maybe 1/10 of a minute or so to put a headset on or less. And if you have a strip of electrodes there, then there you go. You've just put on an EEG system. Also, the hardware cost is going way down. So right now you can buy a conventional BCI for maybe $1,000. There are some systems online that you can get. And the reason I put these lower numbers here is I know that Dr. Pineda recently had one built for just a few $100s. So you can get them. It's getting much cheaper. Hardware costs are going down. The main limiting factor is simply that nobody's building these. In other words, if they were pumping these out at a very large scale, the cost would go down considerably. And also developer support. And admittedly, this is a more subjective thing here, but I just sort of made up figures for support available if you wanted to design one of these things, where 1 to 5 is just a subjective rating scale and 5 means there's a lot of support. So if you're developing, say, an interface involving a gamer mic and you want to get that to work with Windows, ample support is available. But as of, say, 1996, if you were trying to develop a BCI, you needed everything in-house. You had to have your own programmers do it yourself, whatever. Around 1998, they started to develop a system called BCI 2000, which was the beginnings of a universal platform for BCIs. It's basically where DOS was in the early 80s. It's rapidly becoming the universal platform because of lack of competition in BCI operating systems. Hint, hint. So you can see that that's rapidly developing. In about 2002, the system became publicly available, and since then its support has skyrocketed, so that there are now numerous development teams all around the world that are working on BCI 2000 and contributing these modules. And so although it's certainly not the case that the support is on the level of more conventional interfaces, it's getting much, much easier to build BCI applications. Okay, so to shift gears a bit from what is a BCI to how BCIs work. What I'm going to do now is present a general schematic, an overview of how all BCIs work, and then I'll present some specific examples with the P300 BCI I showed earlier, and another approach called the mu BCI, and then some other systems, and then I'll talk about some future directions. So BCI requires the following. You have to have at least 2 electrodes because you're measuring the voltage difference between 2 places, an amplifier designed for EEGs, a mediocre personal computer, and this is another thing that is a misnomer in the field. Many people have the view that this requires substantial computing resources or a supercomputer or at least a very good computer. We had a mu BCI running on a K5-based system several years ago. So even a mediocre computer or even a lousy computer by modern standards can handle a BCI. You need to have an A to D card in the computer, and you have to have software, as I mentioned. All BCIs have at least 4 components, and this slide sort of structures the next several slides, so I'll talk about this for a bit. The first is signal acquisition. So you see from this image here, this is from an article from John Walpaugh and colleagues, a review in 2002. The first component is signal acquisition, which is recording something from the brain in the first place. Usually this is done by EEG mounted outside the scalp. The next is feature extraction. So the raw EEG signal is very noisy. Most of the stuff you get in raw EEG is useless, and so you have to isolate certain features that are of interest. Next, you pass that along to a translation algorithm, which looks at these features and translates that into an output, such as a yes or a no, or moving a robot arm, or whatever. And then finally, and most neglectedly in the field, operating environment, which governs not only how stimuli are presented back to the user, but also governs the user's task structure, what exactly the user can do to influence the environment, what the user might be doing in addition to running a BCI, and so on. And so, as I mentioned before, signal acquisition is an area of moderate progress. There's a lot of work on new sensors, and there's a tremendous amount of work on the middle too, which is largely a math and signal processing problem. So, for example, they have frequent data analysis competitions in the BCI field where they'll take a set of data from a P300 BCI and sort of throw it out there for people to try. And it's a fairly easy project to outsource because there are a lot of people out there who know math or signal processing. You don't need a lab. You really just need access to a web page. Whereas coming up with a new sensor is relatively difficult, and in particular, coming up with a new operating environment in a sense is the hardest because it requires the most integrative knowledge of different things. In other words, you can come up with an improved neural network to classify P3s without really knowing much aside from the underlying math, and the operating environment is sort of falling behind, as I'll get to. So to go into this in a little more detail, in acquisition, the user performs a task that has a distinct EEG signature. And this is, of course, structured by the operating environment, what task they do. And next, salient features are extracted from the EEG, and a system uses these to determine what task was performed. And finally, the BCI presents feedback to the user and forms a message or command. And this loop continues. And so one of the interesting questions early on in BCI development was how do you turn a BCI on or off? And there was this thing called the Midas touch problem, which is the problem of you sort of paying attention to something else or recalling a time that you played tennis as a kid, and that gets interpreted as a message. And so now there's been a lot of work in how to turn BCIs on or off, that there's a certain thought sequence that would turn them on. So to give an example with the P300 BCI, I already described the environment. The environment is, you see a matrix of different options, and it doesn't seem to matter if these options are letters, words, pictures, whatever. It seems to be pretty much stimulus independent. You pay attention to a certain stimulus and silently count each flash while ignoring everything else. So for example, the top 2 images illuminate the letter K. The bottom 2 images do not. So here's a little do-it-yourself thing. So just to get an idea what it's like to use a BCI, please silently count each time the letter K flashes. All right, so that was a rather mundane experience, but you get the idea that if you had an electrode cap on and if you were complying with the friendly experimenter, you would have produced a P300 in response to the K and not to the other flashes. So in terms of acquisition, remember that I mentioned that noise is a big problem with BCIs. It used to be a fatal problem, and now it's much less of a problem. So this image here shows raw EEG from a field setting, and you can see there's a huge nasty-looking thing right in the middle, and that's eye blink. So if you look, you can see that VEOG and HEOG, which are measuring eye activity, show very strong activity. And if you look more right around there, you can see that creates some activity in other channels that might have been misinterpreted as a signal. So one of the issues with the real-time BCI is it used to be that if someone blinked, you would have errors, or you just have to throw out that data completely. You just recognize the blink and say ignore anything. But with newer techniques, such as independent component analysis, it's possible to remove the contribution of the eye blink from the EEG data and be left with the clean EEG, the artifact-free EEG. Another example of a noise source that ICA is excellent at removing is you see in the middle in channels T7 and T8, which are right here on the temporal lobes, there's a high amount of noise. There's a lot of 60 hertz noise and EMG activity that may be caused by jaw clenching or other sources. And that's also something that's very easy to remove with ICA. So that might have been misclassified as a signal, and it's just an example of one of the challenges you have in cleaning up the signal. And rather than throwing out noise completely, just sort of removing the contribution of noise and still getting a signal from the remaining data. And then extraction. So what exactly is it that you're looking at? So again, the P300 only occurs after target flashes. And so this is a graph showing what a P300 looks like. The red line shows the response to target flashes, such as the row containing the letter K, and the blue line shows the response to non-target flashes. And this is recorded from the parietal area right about here, parietal midline, which is involved with, among other things, spatial perception and attention. And the x-axis shows time after the flash onset. So you can see that for the first, say, 200 to 300 milliseconds, you don't see much of a difference. For example, there's a big negative deflection after about 200 milliseconds that looks about the same for target and non-target flashes. And that's occurring in part because your attentional mechanisms have not kicked in yet. In other words, this is very early on where you're just sort of recognizing the signal and have not yet made a determination about whether that's a target or a non-target. As you get later in the visual processing stream up against this parietal area, you start to see this big separation between the two graphs at about 300 milliseconds. And here's another image of this from a field setting. You can see in this one it was slightly later that the P300 occurred. But the reason I put this up is that this was recorded from about the noisiest environment possible. Much noisier than hospitals. I've been in much noisier than here. And this was at the Next Fest Expo in 2004. So Wired Magazine and GE threw this expo of futuristic technologies, sort of a mini World's Fair, and they asked if I wanted to go and see the flying cars and spacesuits and stuff, and I said, yeah. And so I was the guy at the World's Fair with, with the electrode cap and the brainwave speller. And so what I did is I had this cap on, and I spelled using the same paradigm I just described. And the reason I did this paper is that I wanted to prove to the BCI community that even in extreme environments, you can get one of these things to work. And so as you can see from the top two pictures, I was constantly surrounded by onlookers. So people were coming and asking me questions. Kids were pulling on my shirt saying, hey, mister, and poking me and this kind of thing. And I can't say that wasn't distracting, but the point is that as you can see from the data, we did have a pretty strong difference there. And more importantly, in terms of a useful BCI, the overall accuracy I got was about in the mid-70s. So if you're trying to choose 1 out of 36 items, of course, by chance, that would be at about 3%. And so something in the mid-70s, it was a little below 80, is certainly good enough for communication. If you can get 1 out of every 5 letters right, other mechanisms might kick in, such as error correction or letter prediction, or, of course, you could have a backspace, or the person reading your message might, not mind some errors. Good question. This particular one is a grand average of the whole study, so it's an average of several hundred different trials. And if anyone's interested, I have the data from single trials, and you can see how horribly noisy it is, but still, you can also see the signal there. Anyway. All right, so that's it for P3 BCIs, and now I'm going to switch over to a different type called a mu BCI. So the P300 BCI is so named because it's using this brainwave called a P300 that's positive and develops about 300 milliseconds after a stimulus of interest. Mu activity instead is a category of brainwaves. So you may have heard of things like alpha, beta, gamma, delta. Mu is a less well-known and more recently discovered one that's at about the same frequency at alpha, roughly 10 to 12 hertz, but occurs over different areas. So whereas alpha is seen primarily over the occipital areas in the back of the head, mu activity is more prevalent over the sensory motor areas, more toward the front of the head. And mu activity is pretty easy to get. All you do is you look at the EEG and you do a Fourier transform on it to get power at different frequencies, and you look at power at roughly 10 to 12 hertz. It turns out that normally at rest, if you're just sort of sitting there doing nothing, you have a large amount of mu activity. It's sort of like an idling wave. But if you were to imagine movement, and again it seems to be that over training people learn to think about movements that they're familiar with, which is interesting in and of itself. So runners tend to think of running, tennis players tend to think of tennis. One person we had who was an archer would think of archery, and without being told. We didn't tell them think about something familiar to you. They would just sort of evolve to that. And so in this, what you could do is simply imagine movement to move the cursor down. So if you imagine movement, that will suppress your mu activity, and that could move the cursor down, or if you just relax, the cursor would move up. So in the image shown here, this is from also from the Walpole lab with BCI 2000, there's a ball in the middle, or a cursor, that moves from the left to the right at a constant rate. So you have no control over that. But you can control the vertical movement through brain activity. And so the Walpole lab has done a lot of studies where they've varied things like the trial timing, how fast the cursor moves, the delay between trials, that sort of thing, which I would incidentally count as an example of operating system development. These are very important issues, and they do matter, as their papers say. More recently, they've been interested in multidimensional control as well, which I'll talk about. So just to review briefly what this looks like, again, a mu BCI can operate with a very simple headband. Precise positioning is not necessary, so we did it where we just put the headband on and we would measure, and it would be off by a centimeter or so, and we'd still pick it up. And it's mainly measuring activity over these brain areas responsible for movement, especially the primary motor area, which is in the frontal lobe, and primary somatosensory area right on the other side there, which is not colored here, but is also involved. So this is what mu activity looks like. So again, if there's a top target, if you want to move the cursor up, you just relax, you don't think about movement, and that tends to move the cursor up. And you can see that there's a large spike in activity, in this case at about 10 hertz, over motor areas. Whereas if there's a bottom target, subjects instead think about movement, and that significantly suppresses mu activity, and that moves the cursor down. Now this was presented back in 1991. This was a one-dimensional BCI. And since then, they've developed a 2D BCI, and here's a video of that. So this is also from John Walpole's lab. So targets appear in one of 8 locations around the outside of the screen at random, so the subject doesn't know where it'll be. And you can see that the subject has less than a second from the target appearance to actually try to figure out what to do. So once the target appears, he's thinking about movement of different hemispheres and different frequencies in order to move it in 2 dimensions. And you can see the response time is pretty good and accuracy is pretty good. One caveat of this system is it required a fair amount of training. So it requires a few dozen hours of training to get to 2D control at this level. And in very new work, the subject that was doing this, incidentally, the subject used in this video was a paralyzed man. He was paralyzed from the waist down from a car accident. So he's not the classic subject for a BCI, but he did have some change in his motor ability and still seems to be able to do this very well. And they very recently got what they call 2.5D. So this is very exciting for those of us in BCIs, that they can have someone go to a certain spot and then either imagine a grasping movement or not imagine a grasping movement. And if they imagine a grasp, the target turns green. So it's not a true 3D system, but it is 2D plus a third axis of control. It's the beginnings of it, and they're telling me that they're continuing to work on this to develop it further. So that was one approach to a mu BCI, and here's another video with a somewhat different approach. The type of BCI I was describing involves just general imagined movement. In other words, the user can use whatever movements seem most familiar to the user, and thus it takes some hours of training. Another approach is to use pre-specified signals. So in this approach, people simply imagine moving their left hand or their right hand or their right foot, and you can pick up that activity. And this has the advantage of not requiring training, or at least requiring less training, but doesn't, at least not yet, doesn't seem to allow the same bandwidth in terms of multidimensional control. So this gives you an idea of the trade-off, in a sense, of training versus not training. So this is from Gert Furtscheller's lab in Austria, which is another top BCI lab. And how this works is the subject is navigating through a virtual environment. So the subject is wearing a head-mounted display at the same time as an electrode cap and still gets clean readings, even though the HMD, of course, produces a lot of electromagnetic activity. And in order to move through this virtual environment, the subject imagines foot movement. And so the paper here is Furtscheller et al. 06, titled Walking from Thought, which is just a great title. And so that's showing the real-time EEG. And this other monitor here with the cross in the middle is showing whether it thinks the user is imagining a foot movement, which is the downward activity, or a hand movement, which would be the left and right activity. And it'll show it again, but it's also monitoring the strength of it. So in this, you didn't have speed. You're only going forward or backward at a constant rate, and the same with turning. But since they're measuring the amplitude of it, you might be able to actually get a more graded signal where you can run or walk or move slowly. So again, I just want to clarify that although this is fairly elaborate, it gives the impression that you need kind of a whole lab and multiple monitors and a big bank of amplifiers and a whole cap. That's not the case. I don't know exactly how many sites they're using, but in most of their papers they're using only a few sites to get that. So this video is available online, by the way, so I won't go through all the credits. All right, so to go on to some other types of BCIs, I sort of focus more on P300 and mu, and so I'll speed up and present the other approaches a bit more quickly. Another approach that also uses selective attention is called SSVEP, or steady state visual evoked potential. How this works is if you have an oscillating stimulus in your visual field, such as you have one letter that oscillates at 6 hertz and another letter that oscillates at 15 hertz, you can tell which of those letters someone is interested in or looking at, even it works independent of gaze, by looking for that frequency in occipital areas over the primary visual cortex. So if you were just to look at, they're not oscillating right now, but if you were to look at these and not pay attention to either one, we would see some neurons would be firing at 6 hertz a second in response to that thing. They're sort of saying, hey, 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 as they recognize that signal. Others would be firing at 15 hertz. However, if you chose to focus your attention to the left or the right image, we would see an increase to the attended frequency and a decrease to the unattended frequency. Here's another example of how to do that. This last one was from Simon Kelly and John Fox and colleagues. This is one that I did that's in press. And this involved 2 checker boxes, 6 hertz checker box there on top and the bottom checker box oscillating at 15 hertz. And then for the interface, I used the same system as you saw for BCI 2000 with their mu BCI. So essentially, BCI 2000 isn't really designed to support SSVEP. I just sort of told it was mu. I said, here are some frequencies, and gave them different frequencies in different sites, and it worked. So it's the same task. The cursor moves from left to right at a constant rate, and by attending to the top checker box or the bottom checker box, rather than imagining movement, they can move the cursor up and down. And this is what the brain activity looks like from such a task. And I know this is a fairly complicated slide, so I'll go over it a bit. So the top 2 images, A and B, are from one electrode site over the occipital lobe, and C and D are from a different site. Panel A here is showing activity when you pay attention to the 6 hertz checker box, which is the thinner line, or the 15 hertz box and the thick line. And then panels B and D are just showing the R squared, the correlation between that particular frequency and the signal of interest, the output. And so you can see there's a large spike at about 15 hertz and smaller spikes at 6 and a harmonic of 12 hertz. And then over the last panel, that's showing a topographic display of that all over the entire head. And so what you can see is that this activity is very clearly distributed toward the back of the head and the occipital lobe. If you had seen other colors elsewhere on the head, that would be bad. That would mean that something's wrong. It's also interesting that this subject, like most subjects, showed a stronger response to 15 hertz boxes than 6 hertz boxes. Why did we choose these 2 particular frequencies? This is a very common question. There's absolutely no precedent. No study has ever been done to look at which pairs of frequencies produce the strongest response. It's a really obvious, important study, and one that I hope to do. Yeah?
If you have things switching on and off, have you checked not to trigger epileptic fits?
Excellent question. The question is, have we checked to see if that triggers epileptic fits? No, we screen subjects for epilepsy, and so we have not run any subject who has ever had a history of a seizure because we are concerned about that. To answer it in more detail, they have a fairly good idea what sort of exact conditions would trigger that. And so I think that this would be safe. Don't test it yet. I think that this would be safe for epileptics if you were really careful to manage the frequencies carefully, talk to the doctor. It depends on the type of epilepsy and such. But that is a concern. All right, so next I have a brief video here. And so as I mentioned, one of the things I was trying to do was demonstrate that these systems can work even independent of gaze shifting in disabled users. And so this is a patient here. That's patient DJ there who has late-stage ALS. And He currently uses this system called Words Plus that navigates with eye gaze. So he's not currently controlling this with the BCI, but this patient is currently spelling. And so this person, although he's unable to make most movements, is very smart. He's a nice guy. He's very quick-witted. He's fun to talk to. And so there's a robot arm in the background, by the way, from another study we did. And so what we did is we went to his house and set up a BCI there. This is an example of what noisy EEG looked like. And so here I'm showing the patient his own EEG. And this is fun to do with subjects. You can show them, here are your brain waves and look what happens when you blink. And I think that's what Melody was pointing at. And so you can see how we have to prep them, put electrode gel. We were using conventional caps at the time. And there's the task. So one monitor displayed the checker boxes, another monitor displayed the task. Why are they not on the same monitor? It's a programming challenge. It's not. The system would have worked much better if they were the same. And so he's trying to move the cursor up in this one, and you can see there he goes. Anyway, so the next approach is called SCP, or slow cortical potential, and this is the one that I mentioned that involves emotional imagery or sexual imagery. So how this works is you have a baseline for a couple minutes where you just sort of think about nothing, you just relax, and then either a tone or a visual cue prompts you to either think of strongly emotional imagery or continue to not think of anything, and that can be detected. And this approach has been developed largely by Niels Bierbaumer and his colleagues in Germany. The main advantage of this is it's been most thoroughly tested with patients, that Bierbaumer and colleagues have been very, very good about getting this to patients' homes and have worked with dozens of patients in field settings. A concern with it is it requires more training than any other approach. So it requires weeks or months of training and also offers very low bandwidth. And so Bierbaumer and colleagues, Femke Niebuhr was the lead author, recently did a study in which they compared this approach versus P300 versus mu, which is another example of a really obvious study that hasn't been done, is within subjects comparisons of different approaches. And what they found was that, in fact, the SCP approach did not seem to be as effective as the other two. So certainly kudos to Niels for exploring that, and his lab is now getting into other types of BCIs. And so in the long term, I'm not sure that SCP-based systems will remain prevalent. Another approach is a mental task BCI, as I mentioned. And so the ones I've shown so far have been EEG-based systems, and this is a newer one involving functional near-infrared. And in this, the subject would relax for 10 seconds, and then to say no would continue relaxing for 10 seconds, or in order to say yes would imagine counting. And you can see that when the subject tries to say yes, you see a big increase in blood flow over this area of the frontal lobe that's involved with working memory and speech production and mathematical stuff. And so this seems to be a promising approach. Again, FNIR is very new, and this is a slow approach. So it takes maybe 20 seconds or so to get a single yes or no determination. But it's very new, and with more work, we'll see. And finally, you can record directly from cortical neurons. So this is the field of implanted electrodes. And the two images on the right show a couple different examples of implanted systems. The Utah intracranial electrode array has a 10 by 10 grid that actually goes in the surface of cortex. So each of those individual pins is poking into your brain. And so the obvious drawback of this is that it's actually damaging tissue. And this has mostly been done, but not exclusively been done, in animals. And the bottom one shows a cone electrode, which is developed by a different group, which is a glass cone that encourages neurons to grow into it. And this is these are a couple examples of implanted BCIs with human patients. So the one image shows a patient with an implanted BCI. This patient is disabled by injury. So he had a knife wound to his brainstem in a knife fight and lost the ability to move below his head and lost some speech and such. And the other image is a patient, I think he was late-stage ALS, but I'm not sure. And in the right one, this was a subject to control a switch, so that it's actually published. What the patient did was press a foot plate. So he still had some residual foot movement. They recorded brain activity while they pressed the foot plate, and that would turn a light on or off. And then the subject would just imagine moving the foot plate, and that would turn a light on or off. And this is a common approach to implanted BCIs, that they all seem to require training, that you have to implant them and get a feel for how individual neurons respond before you can actually do anything with it. This is a very new image from my friend Kai Miller at University of Washington. showing different activity across different subjects while they made a hand or tongue movement. And so this is with an implanted grid, ECOG, and you can see that hand versus tongue movement tends to affect different areas of the brain. So in comparing BCIs, there are a great many different axes along which you could compare them, and I'll talk about this briefly in the next few slides, and then I'm done. But the idea that I presented, that sort of, certain BCIs are faster than others or require more prep time or whatever, it's often more complicated than that. It also depends on what kind of information you want from the user's spared abilities, a variety of other factors. Also, information throughput turns out to be not necessarily the most important thing. In other words, a lot of patients will choose to maximize accuracy over the number of things they can send because they're very frustrated by errors. So, another big thing with information throughput is, are you matching the user's desires? So if the user wants to make himself a cup of coffee and you give him the greatest speller in the world, that's not directly helpful. He could ask for it, whatever, but that patient may prefer a much lower bandwidth robot arm to make coffee like the one that we made, rather than a speller that may take a long time to ask for coffee. So in getting into future directions, and I'll just talk briefly about this because I wanted to talk about this a little at Microsoft, I like this quote from John Walpaugh emphasizing the interdisciplinary nature of the field. So again, it's not really a field that you can get into with only one specialization. You need to have a lot of different people with different backgrounds working together. And in particular, having been from the cognitive science department at UCSD, I must comment that this is quintessential cognitive science. Anybody that likes cog-sci, it's hard to define cog-sci without having these facets in it. And so it was really fun for me, and still is fun. I teach a class this summer at UCSD on BCIs. It's great to have these students here from completely different backgrounds who have a very different take on what BCIs are. So this is the worst way to look at future directions, which is replacing conventional interfaces for conventional users in conventional settings. Right? So this is not the future of BCIs. And yet, again, just like many people have certain views on how BCIs work, a lot of people use this to sort of reject the idea that BCIs are imminent, which they're not. So I'm not going to tell you that everybody is going to be wearing BCIs soon, that they're going to replace keyboards or mice or whatever within a reasonable time frame. So the idea that this is what's going to happen anytime soon is inaccurate, but it also may be clouding the issue. In other words, there may be other opportunities if you start to change some of these assumptions. For example, disabled users, well, they can use BCIs. So that's one example, that conventional interfaces for disabled users is very viable. Another one is replacing conventional interfaces for healthy users in specific environments. And so the fun thought experiment here is to think about what are settings in which people cannot use a conventional interface, such as a driver or a surgeon, a soldier in the field, a mechanic. There might be a lot of situations where your hands are busy, and you also may not be able to use your voice, either because of background noise or you don't want to be overheard. And all of a sudden, the very low bandwidth information you could get from a BCI might become more viable. And also in supplementing conventional interfaces. So again, this notion that people are going to sort of wear BCIs instead of using keyboards, which is really ridiculous and won't happen for a long time, clouds the issue where you could also look at it in terms of using a BCI to supplement a conventional interface. And this is where I see a lot more opportunity in the near future, where if you're already using a keyboard and a mouse, could you get some additional information from a BCI that might supplement that? The critical study or series of studies that needs to be done is, in a sense, what's the distraction quotient of a BCI over time. So if you first start to use a BCI, I doubt that you could type and use a mouse and use any type of BCI effectively. The total bandwidth would be much lower. But when you're using a keyboard, why do you also use a mouse? So why not just send everything via a keyboard? There's a serious cost to moving your hand. You guys have probably studied this quite thoroughly, to moving your hand. But the mouse offers certain functionality that can't be accessed easily via the keyboard. So a keyboard can operate a drop-down menu, but mice seem to be better at that. And so similarly, there may be some parallels with BCIs, where a BCI type of interface may lend itself toward other types of things. Attentional computing, for example. If we can tell what region of the screen or what event is of interest, that's very useful. And so to get to this question of why bother, got 2 more slides, I think. One is bandwidth, of course. So comparing, say, a gamer headset to a headset that's using electrodes. One reason is bandwidth. So to get at this question of why put something on your head, any of you who have played games know that before the development of gamer headsets, and even to some extent today, you have to hit enter to type something. And so a lot of times you're going through and you play your game and you want to convey something to a teammate or respond to a taunt or throw your own or whatever, and you hit enter and you start typing, and then all of a sudden some game event occurs that you have to respond to, and you either hit the wrong keys and don't actually send anything because you're still in typing mode, typing out a message, or you go and you hit enter and you go back, and in that half a second you have been shot, nuked, stabbed, overrun by zerglings, shot down, whatever. So that's one example, that the microphone, and I'm referring here not to the headset, that the headphones themselves are an output device. I'm referring only to the microphone component. Why is it that people widely use these devices? Well, in part it's providing you supplemental bandwidth, that whether it seems that way or not, a keyboard is not even remotely providing the bandwidth necessary to control most modern computer games, and that's a major source of overload. The same with the Xbox controller. I mean, why are there so many buttons and so many different combinations on there, so many different controls? Because there is an ongoing demand for more information throughput. But another important facet of this is cognitive overload, that if you're typing and you're in the middle of doing essentially a motor task and a visual attentional task, sending language, saying something, is utilizing brain areas and cognitive resources that have not been tapped by these conventional approaches. So I would hypothesize, for example, that trying to use a keyboard while imagining left or right hand movement is not a very smart way to hybridize, to combine a BCI with a conventional interface. But again, doing that and getting background information on what region of the screen you're interested in or what events caught your attention, that could be very useful. Another one would be error monitoring. I was talking briefly about this with Jonathan Gruden, that if you type a word, for example, if you type out BCI in Word, it will underline that in red because it doesn't recognize that acronym. Well, what if you had a system that could tell on a single trial basis whether or not you think that you just made an error? That's actually quite easy. And so I'm now blending into things that are not strictly BCIs, other EEG-based applications. But then you could do two things. One is, if it thinks that you made an error, it could automatically pull up a list of corrections without you having to go back and right-click it. Or if it detects the absence of an error, it won't underline it in red in the first place. And I know this is something Eric Horvitz here is very interested in, is what information can you get that's not necessarily intentional communication, but that might supplement other information to improve an environment. So other groups here are working on, as you become fatigued, fatigue is also easy to pick up. Maybe you would make stimuli bigger or louder. You would otherwise account for the user's cognitive and emotive state. Another one might be privacy. So if you speak or you type out a password on a keyboard, that can be seen. And convey otherwise unavailable information. So here I'm getting to things like neuromarketing, where you might be able to tell someone's response in real time to a certain event, or whether they're going to remember something that would not easily be, it can't be determined easily or even at all through other sources. And of course the idea that they might just be novel, that people might want to wear them, gamers might like it just because it's cool. Public perception is another major catalyst of how BCIs develop. Of course, there's a great deal of worry in the field that they will be seen as Orwellian or invasive. The thing that scares me is sort of the analog of the Raelians with the cloning thing. So few people remember that several years ago there was a group in Canada that claimed that they could clone people, and it was a religious cult that didn't really do anything but ended up getting a great deal of bad publicity for the cloning people. So, I won't go into this. So there are several different ways to improve BCIs, and again, I think the main one is building hybrid BCIs. I won't go over this in detail. I just wanted it up there for the slideshow for later. But a major one is hybridizing them, combining them with other BCIs, other interfaces, and developing improved operating systems based on that. And so there are a lot of applications for BCIs or similar systems. And I say this as my last slide or near to last slide just to encourage discussion. So I think I have some ideas where BCIs or related technologies are going, but want to develop this through dialogue with you. So I invite you to develop the killer app for BCIs. Here are some examples of ones that I threw up, alertness or attention, error monitoring, as I talked about, a variety of things, and including toward the bottom, biofeedback and training that's already popping up. There's some companies that advertise training this for kids and such. Anyway, I want to conclude by thanking a lot of people who helped me in the various work presented here. On the bottom is a picture of a lot of the BCI people from a conference recently. If anyone wants to get these video clips, here they are, and since this is being recorded, I can just gloss through this. And finally, here's some websites with more information about BCIs. And that's it. Thank you.